Elimination reactions of alkyl halides. E2 elimination. Under certain conditions, alkyl halides can undergo elimination reaction to give alkenes. For example, when 2-bromopropane is reacted with methoxide ion in methanol, the major product formed is the product of elimination, propene. Based on our understanding of nucleophilic substitution reactions, we would have expected 2-bromopropane to undergo nucleophilic substitution by SN2 mechanism and give methyl isopropyl ether. Elimination reactions of alkyl halides. E2 elimination. There are two reasons why elimination is favored over substitution in the reaction of 2-bromopropane with methoxide ion in methanol, giving propene as major product. 1. In protic solvent methanol, the nucleophile methoxide ion is weakened due to solvation. 2. Methoxide is a strong base and hence able to pick up the acidic proton attached to the beta carbon more efficiently than attack the alpha carbon due to steric hindrance. Reaction mechanism. Even as the beta proton is picked up by the methoxide ion, the CBr bond breaks and the Br- leaves, resulting in the formation of propene in a single step. Concerted reaction mechanism. This mechanism is called E2 elimination. When secondary alkyl halides are treated with strong anionic nucleophiles, which are also strong bases, E2 elimination will dominate. Elimination reactions of alkyl halides. E2 elimination. When primary alkyl halides like bromopropane is treated with methoxide ion in methanol, the major product is methyl propyl ether. In primary alkyl halides, the alpha carbon is less hindered and hence the nucleophile is able to access the same with relative ease to give nucleophilic substitution products. However, when primary alkyl halides are treated with strong and bulky bases such as potassium T butoxide, then elimination occurs to give alkenes as major product. Bulky base is able to abstract the proton from the beta carbon more easily than attack the alpha carbon due to steric factors stemming from the bulk of the base. Elimination reactions of alkyl halides. E2 elimination. Hindered primary alkyl halides like 1-bromo-2-methylbutane, when treated with a strong base, a mixture of elimination and substitution products could be obtained. The mixture products will depend upon the degree of hindrance encountered, the type of base, and other conditions like temperature, etc. When tertiary alkyl halides like tertiary butyl bromide are treated with a strong base, the major product will be elimination product 2-methylpropene, since the halide is too hindered to undergo SN2 reaction. Regioselectivity in E2 elimination. Zaitsev rule. Zaitsev rule states that when two different alkenes could be obtained due to elimination, the major product will be the more substituted alkene. When 2-bromobutane is treated with methoxide ion, 1-butane, cis-2-butane and trans-2-butane are formed. Cis and trans-2-butanes are the major products. Trans-butane is formed to a much greater extent, suggesting stereoselectivity. When 2-bromo-2-methylbutane is treated with methoxide ion in methanol, the major product is the more substituted 2-methyl-2-butene. Zaitsev rule may not be obeyed due to steric factors. Sometimes steric factors play a major role in determining the product mix in an elimination reaction than Zaitsev rule. Example, when 2-bromo-2-methylbutane is treated with a relatively non-bulky ethoxide ion, the major product of elimination is 2-methyl-2-butane. The base is able to abstract the proton attached to carbon 3 with relative ease. However, when 2-bromo-2-methylbutane is treated with bulky T-butoxide, the major product of elimination is 2-methyl-1-butane. In this case, the bulky base is able to access the proton attached to carbon 1 more easily than the one attached to carbon 3. Stereochemical requirement for elimination reactions. 2-bromobutane will undergo elimination to form trans-2-butane only in the conformation in which the sp3 orbitals bonded to bromine and hydrogen have anti-periplanar relationship. The anti-periplanar geometry facilitates the abstraction of the proton by the base without steric hindrance from Br. Also, the developing p orbitals on account of elimination are aligned parallel to each other in this conformation to facilitate the efficient formation of the pi bond by lowering the energy of the transition state. A syn periplanar geometry between hydrogen and bromine will create a repulsive interaction between the base and Br and will raise the energy of the transition state. Stereochemical requirement for elimination reactions. Reaction of trans 1-chloro-2-methylcyclohexane with methoxide gave 3-methylcyclohexene as the major product. This is due to the fact that elimination can occur only in the conformer 2, in which the chlorine and the hydrogen have the anti-periplanar geometry. Since this conformer is a higher energy conformer compared to conformer 1, the rate of elimination is slow. On the other hand, when cis 1-chloro-2-methylcyclohexane is treated with methoxide, the major product of elimination is the more substituted 1-methylcyclohexene. This is due to the fact that elimination occurs in the most stable conformer 1, in which the chlorine on carbon 1 and the hydrogen on carbon 2
have anti-periplanar arrangement. The rate of elimination is faster compared to the trans isomer since elimination occurs in the most stable conformer. Elimination reactions involving E1 mechanism. Just like nucleophilic substitution reactions, elimination can also occur through two different mechanistic paths. The path involving the formation of a carbocation intermediate is known as E1 mechanism. Typically, E1 reactions occur under the same conditions in which SN1 reactions occur, in the presence of weak bases and polar aprotic solvents. Usually, both the elimination and substitution products are formed. The proportions depend upon the type of alkyl halide, nucleophile, temperature, etc. When tertiary butyl bromide is reacted with water, both elimination and substitution products are formed. The mechanism involves a common carbocation.